Right. Basically, guys, this is not a very complex apparatus. I mean, there's nothing much to precisely handle and all. It's basically a narrow glass tube. It should be a narrow tube, right? So we will come across, like, we will discuss why it should be narrow, all these things. So it's like important facts and important facts. It should be a narrow glass tube. Narrow glass tube, which is mounted. Mounted means which is somehow placed on a certain linear scale. Like, how can you place? You can, like, by just mounting it on, you can, there is two holes here usually, right? So you'll have to send a rubber band or else a string or something, and you will firmly fix it. In Quill's tubes, there are obviously, if you do this experiment in schools and all, so you might have seen there's a small two holes. Using that small holes, it's fixed by using a string. By sending the string, you just fix it. You can put a knot and fix it so that it doesn't move, right? You should be able to, like, incline this, right? This way you will have to be able to incline this. And when you incline this, this shouldn't change its angle and all. You need to firmly fix it. Okay, let's assume it's firmly fixed. Right, now what have we done? We have taken a linear scale. This is what? This is a linear scale. Linear scale, right? To this, we have fixed a narrow tube. Narrow tube. Fixed a narrow tube, right? Fine. Next, what you need to do is, using a certain known length of, using a certain amount of mercury, you need to trap some dry air. By using certain amount of mercury, by inserting certain amount of mercury, you need to trap certain amount of dry air. I'm going to include certain amount of mercury. I'm going to trap dry air. I'm going to trap dry air. Dry air. We can do that, right? So, like, very simple. Somehow you just have to very carefully insert some amount of mercury. In that case, it's going to definitely trap some amount of air, dry air. That's nothing bigger process, right? Very basic, simple process. Right, that's done. Now you need to take some readings, and then you have to incline it somewhat. First of all, you need to slightly incline it, and you have to take some readings. First reading is, like, there's no order, right? But still, you need to take some readings. This is the reading first, as I would say, the length x, the mercury height, the column mercury column height, the length of the mercury column, x, length of the mercury column x. Next, what you need to measure is, can't you measure the length? It's very easy, right? You just have to see, okay, this and this, right? By using somehow, by means of a, without making any parallax error, you need to place your eye exactly and measure it. Right? It's not going to change, right? The length of the mercury column is not going to change when you make it horizontal or vertical or anything. It's always going to be constant, because it can't vanish, right? I mean, even if you make it horizontal, vertical, it can't compress. It's a fixed mass. Always it should be x. Remember that. And then you need to also measure this length L, simple L, the length of the trapped air column. You need to also measure the length of the trapped air column. Length of the trapped air column. Right? Next, what you need to measure is this total length. The total length of the linear scale, right? Linear scale. Can we measure it by keeping it straight? What measurement are you referring to? Is it length or x or L? L and x can be measured by keeping it. X can be, because like x is not going to change, right? Like, even it doesn't matter even if you make measure x in horizontal, like go turn it upside down or anything. Because why? Will the like will it get compressed or stretched? No, because it's a mass. It's a certain mass. The volume of that is not going to change. Incompressible liquid. It is an incompressible liquid fluid. If it is incompressible, like the volume of that can't change, right? Like the length can't change because this is constant. Area is constant. Cross-section area is constant, which means the length should always be constant. It can't change. Think about that and see. When you change it, can it get compressed? No, incompressible. I guess it's clear. Fine. Now, what you need to do next is, what have we done now? We found this x, L, capital L. Also, you need to measure this height h. You need to measure this height h. Right? You need to measure this height h, this perpendicular height. H. Can't you find that? It's possible. It's possible. You can find it. You place it on a table and then firmly keep it, and then find by using a set square or something. Like say you can keep a set square and measure the height. It's fine. It's not going to be an issue. Right? Okay. This is theta. Let's say this is theta. Now, what have we done? Now you need to understand what we are going to do in this experiment. Be inside the experiment. What are we going to find? Verify Boyle's law, right? Verify Boyle's law. We need to change the pressure and see what happens to the volume. Or else we need to change the volume and we need to see what happens to the pressure. Somehow both pressure and volume is variable. They can change. Now, how will you change the pressure, for example? So the gas, who is the gas here? Yes, exactly. This is the gas, air. Air is the gas trapped, right? I'm going to apply the Boyle's to the air, Boyle's law to the air. Air which is trapped inside this Quill tube. How will I change the pressure acting on this air column? There is an answer. Can anyone else try? How can we change the pressure inside this air column, placing in different heights? I mean, like you're changing this height. You're changing this height. Is that the case? Yes. Exactly. Simply, what you do is you change the inclination. Right? You change the inclination. Right? Just change the inclination. This inclination, right? Not this inclination. This inclination. What happens then? What happens? The pressure acting will change. When the pressure acting on this changes, as a result, what happens? As a result, what happens is the volume changes. This will come down if you kind of increase the inclination, horizontal inclination. This will come down, and the volume will decrease. Pressure increases, and volume will decrease. So now you need to understand what we are going to do. We are going to change the pressure, and we are going to see what happens to the volume. We're going to change the pressure. How are we going to change the pressure? By slightly making it, inclining it. I mean, increasing the height. This height. Right. Clear. In that case, what happens is the volume changes, volume decreases. Fine. So how do we verify that Boyle's law is correct? Yes, that's the problem here, right? That is what we need to figure out. Right. First of all, let us write an expression for the pressure inside this air column. Pressure. Let's write and pressure. Okay. This is exposed to the environment, right? Which means this is pi ATM. So this is theta. This is theta then. So pi P, the pressure inside this air column is P pi plus x cos theta. Mercury centimeters. Mercury centimeters. I'm not going to write rho g and all, right? Rho g, because I'm not going to write rho g. It's at mercury centimeters. How was this understood? Because like the pressure inside the air column is the atmospheric pressure plus need to get the vertical height. This is like, you know, right? So you can't deal with the slant heights. You always need the vertical height. Now, okay, this height. What is it? X cos theta. X cos theta. That's the vertical height. X cos theta. Instead of cos theta, what can we write? Because like measuring cos theta and all, it's not going to be a practical thing. Cos theta, because you can measure instead of cos theta adjacent over hypotenuse. But cos theta is what? Adjacent. They consider this triangle adjacent over hypotenuse. Adjacent over hypotenuse. Exactly. Now this replace it here. P is equal to pi plus x cos theta is h over L. H over L. H over L. Pressure of the liquid air column is pi x plus x over x into h over L. Pressure is found. Volume of the air column. How will you find? Cross-sectional area is A. Cross-sectional area is A. In that case, A into L. A into L. A into L. Right? A into L. Right. The most important part, we have got an expression for the pressure inside the air column. We have got an expression for the volume of the air column. What we need to do is we need to verify that Boyle's law is true. To verify this Boyle's law is true, we use a nice trick. That is, like, you need to know. Math students, of course, they know this method. The method is when you are supposed to verify something, verify or show something, show that they assume that it is true, and they prove it, and then they show it is true. It's like this. They assume it is true. Actually, what they are supposed to do is they need to show something. They're required to show something, show a certain equation. For that, what they do is they assume it is true, and they do solve a bit, and they show a universal truth. A universal truth. Okay, 1 is equal to 1. Likewise, it's just example, right? We're going to do that. We're going to assume that Boyle's law is true, and I'm going to, based on that, we're going to show a universal truth. Very important. Let's assume Boyle's law is true. Then what is, if it is true, then PV product should be equal to what? A constant called K. If it is, if the Boyle's law is true, PV product should be equal to K. So shall we write P? P is equal to what? 5 plus XH unit AL. Okay, now guys, 100% required. The concentration is required because if the experiment is given, you definitely need to prove this, right? You need to do this simplification. It's not going to be very easy, right? Not as easy as other experiments. There is a bit of simplification. Attention required, right? Right. My requirement is I'm going to subject H. I'm going to subject H. Don't ask why, because we will see why I subjected H after I subjected it, and I'll tell you why. I'm going to, my target is to subject H. For that, what I'm going to do is I will send this down. I will send this to that side. I will divide this all the terms by X. I will multiply all the terms by L. I have subjected H. So this is going to be what kind of a graph? Y is equal to mx minus c. Y is equal to mx minus c. Y is equal, sorry, mx, mx minus c. What is x? What is the variable? X. Sorry. X means like the independent, not this x, right? Not this x. X means like the independent variable. What is the independent variable? The length L. This length L. What is the dependent variable? Height h. But actually, if you think in detail, you will understand that height h is the one you change. As a result, what changes is L. Height h is what you change, because like I told you, right, we are going to increase the pressure by how? By making it more inclined, which means if I'm going to increase h, what we do is we increase h. As a result, what happens is L changes. So actually what it should be is h should be the x variable and y should be L should be the y variable. But I have taken it upside down, right? I have taken h to be as the y variable and x to be as the L variable. Why is it? And there is a reason. There is a reason. We will learn it under the important parts, under important facts. For the time being, what I have done is 100% correct. What I have done is 100% correct. So, okay, L changes. L changes how? When we change x. When we change h. Fine. Right. If you draw a graph, it's going to be how? If you draw a graph between, x-axis, who is xr? If you draw a graph 1 over L and h, we're going to get a positive graph, but a negative intercept. Negative intercept. Positive graph, negative intercept. So what is the gradient in this? Gradient. Okay, if you see the gradient is constant. But in the equation, what is the gradient? KLXA. We know that x comma a and L are constants. We know that x comma a and L are constants, right? So this x is a constant, the cross-sectional area is a constant, this is a constant. But when you draw the graph, it's like this. How will you draw the graph actually? How are you going to draw the graph? You have to take few set of readings. You need to increase this. You need to change this height. You need to change h1 and find l1. You need to further change h2. And then what happens? L2, h3, l3. Likewise, take points and mark the graph. When you mark the graph, you will see the gradient to be constant. You will see the gradient to be constant. If the gradient is constant, then obviously this and this is constant. XA and but gradient is constant. Therefore, since the gradient is constant, all these should be constant. X, A, and L constant already. K should also be a constant. Therefore, K should be a constant, which means we have proved that the product PV, which is K is a constant. We have proved that K is a constant. What Boyles told us was PV product is constant. What we did was we got the PV product. And we proved that K is a constant, which means Boyle's law is verified. This is one way this is the way how you could verify the Boyle's law using Quill's tube. Once again, quickly, we found the pressure, right? We found the volume, right? I assume the Boyle's law is true. If it is Boyle's law is true, then PV product is equal to a certain value. We don't know whether it's constant or not. We will see. If it is constant, if it is a constant, then Boyle's law is true. This K should be a constant according to Boyle's law. We'll see whether it's constant or not. Right. Okay, I wrote the P and I wrote the V. I did a simple simplification and I got what are we changing? We're changing heights, and what changes as a result is L. So I drew a graph. The graph is going to be against 1 over L and H. The graph is going to be a straight line. It's going to be a straight line which has a negative intercept. But like obviously, what is the gradient of this equation? Gradient is this part. KLXA. But you know, L, X, and A is already, we know that it's constant. And also, if you see the gradient also is constant. The gradient is constant. All these should be constant. Obviously, L, X, and A is already a constant. Then definitely K should also be a constant. Right? K should also be a constant. So we have proved that K is a constant, which means PV is equal to a constant, which means Boyle's law is verified. The thing is, now we are going to move on to the important facts, right? Write down important facts regarding the experiment. Important facts regarding the experiment subtopic. Important facts regarding the experiment. Right. Now let's move a bit quickly, right? So why do you think why did we change this X? Why did we change this independent and dependent variable? Actually, L should be here, it should be here, right? That's how it should be. Why did we change the independent variable and the dependent variable? Actually, H is the independent variable. H is what we change. L is the dependent variable. That is because like L is what it becomes, like what it changes due to the change of H. So actually, H should be the independent variable and H should be the dependent variable. L should be the dependent variable. We have written it in this way. That is because then only we can find the atmospheric pressure from the intercept. The intercept is what? Phi L over X. The intercept is minus phi L over X. If we subject H only, phi is going to be here. If not, what happens is phi is also going to be here in the gradient. And then like we do not know the value of phi. Things are going to get complex when we find the gradient and K. And also like now this is very easy because why? So here there are no unknown factors. L is known, X is known, A is known. So we can easily find K if required. And also based like if the pi comes in the intercept part, and also if we have to find the pi, we can use this experiment to find pi also, right? The atmospheric pressure. We can easily find the atmospheric pressure by finding the intercept. The graph, we can find the point where it cuts the x-axis, y-axis. It's the intercept. The intercept is equal to what? Intercept is equal to IL over x. So pi is equal to intercept into x over L. X and L are known. You can easily find pi. So basically, this is done. We interchange the independent variable, the dependent variable, in order to find the atmospheric pressure from the intercept. You can interchange and write and see. You can subject L and write and see. You will see pi is not going to be in the intercept. It's going to be complex. The equation is going to look complex somewhat. It's not going to be very convenient for us, right? So that's the reason, right? So when we change the independent and the dependent variable, we can easily find pi from the intercept, right? Okay. The next thing, right? So I will ask you a simple question, like try to be interactive, right? So like, what will be the range of h? From what point to what point can I change h? Is it from horizontal to vertical, or else is it from inverted position to horizontal, or else is it from inverted position to upright position? What is the range of h? What is the range of h that I could do this experiment to? Inverted to upright. It should be inverted to upright, right? Invert, because like even if it is inverted, the volume is the highest. When it is inverted, the volume is the highest, and when it is upright, volume is the least. When it is inverted, pressure is the least. When it is upright, pressure is the maximum. So from the least pressure, sorry, like this is inverted, this is upside down, right? So I mean, it is interchange, right? So from the least pressure are moving up to the maximum, then what happens is from the highest volume, it decreases 1 over L, right? So anyways, that is the range, right? You can change this from inverted to upright. Inverted to upright, which means the range is minus L. It can be minus L. It can be from minus L to plus L. When you make this upright, H is going to be what? H is going to be plus L. When this is inverted, H is going to be minus L. My mercury won't spill. Why? Because you know, right? We did a similar experiment question. The atmospheric pressure will balance this. Right? Atmospheric pressure will balance. Atmospheric pressure is acting from the below, so it will not fall, because like this is a narrow thing, right? Narrow thing, not a, if it is a somewhat of a higher surface area, the cross section area, it will straight away get down. That is some other story, but still these are narrow tubes, right? Most of the cases it's not going to spill, right? Now I will ask you a further simple question. What will be the graph that I get if I draw L versus H? Think about it. If I like, it is 1 over L versus H. I will give you a small hint. Is it going to be this curve or this curve or this curve? A, B, or C, or D, or E? Which curve? Why is it A? Answer is A. The reason is H. H measures what? H measures H. When you change H, it like the what changes is pressure. Pressure. L L measures what? The volume. So pressure versus volume. It's going to be this curve. Right. I equal M over X. Yeah. Right. So that's clear. So write down. And actually, this is not the curve, right? This is not the curve of H versus L because like actual curve is this, right? Actual curve is this. You can draw this also. I will give you time, right? So it's like this. Actual curve is because like H varies from plus L to minus L, right? H can be varied from plus L to minus L. In that case, it's going to vary as this. It's going to vary as this, right? Now, next problem that I'm going to ask from you all is, why do we use a narrow tube? So in most of the cases, when I was giving you the note also, I was saying narrow glass tube. Why is it narrow? Narrow means thin. We could have used the to get accurate reading. Narrow glass tube and accurate reading. What is the link? We use a narrow tube because in order to trap a longer length of it's like this. If we use a narrow tube, right? If we use a narrow tube actually, right? For example, let's assume with this mercury column, we were able to trap this amount of a air volume. The volume of this is V. Now let's assume I'm going to use this amount of a very a glass tube with a higher width. So this X amount of mercury liquid column can trap V amount, which means like the same volume, right? Same volume of mercury column, it will not be able to trap this much. It will be able to trap only this much. This is V. This is V. This is V. Like to do the experiment, we have to have a longer length, right? Then only when we change this thing, when we increase the pressure, this keeps on decreasing. Then only we can do the experiment. If it is very small, if the gap is small, like when we turn it, straight away it goes and collides on the surface, right? So you do not have much space to do the experiment, the range. So the reason is in order to trap a longer length of the air column only, we use a narrow tube. Hope you understood that, right? Okay. Important point, right? That is this problem. Like I have seen this experiment 1 or 2 times. In all the experiments, this question was there. To be honest, this question was there in all the experiments. Like this experiment was repeated around 1 or 2 times. Right? I can't exactly remember how many times. Right? More than 1 time it was there. But still, in all the attempts, this question was there, as I remember. Yeah. That is, instead of mercury, why can't we use water to trap the air column? Instead of mercury, why can't we use a water column? Think about this and answer like in a physics way. One is, if anyone still can answer it, one is what exactly? Yeah, water is highly vaporizable. Yes, exactly. Water is highly vaporizable. Water can evaporate. When water evaporates, a lot of issues are going to be there. When water evaporates, the pressure is not only due to high, the pressure here is due to water vapor also. Saturated water vapor. You learn in a few more sessions. Saturated water vapor. When water vapor evaporates, here like not only the pressure is due to the atmospheric pressure, but also the water vapor, saturated water vapor pressure, and also the length changes because like water vapor evaporates, right? The length will change. This is not going to be this is going to be an issue. One thing, evaporation. What is the other thing? In order to exert a considerable pressure on this air column, in order to exert a considerable pressure, you might need a very long air column, sorry, water column. Mercury is high density, HROG, rho is high. So therefore, a higher pressure is exerted. So you can exert a large pressure on this air column. But in order to get the same pressure P, in order to get the pressure P due to this X air column, X mercury column, you have to use a very high, very longer length of H water, because rho W is very less than mercury. Mercury is 13,600 density. This is 1000. So you need a very high water length. If that is the case, things are going to get worse. Why? Because we have a limited area to do the experiment, right? In that case, it's not going to be a good thing. Better we have a smaller. If we can give a higher pressure, if we can exert a higher pressure by using a small length of the liquid, it's going to be better, right? Actually, it's better. That is another one. Finally, what? Also, the water is transparent. These are simple things, right? Like, think about this. Water is transparent. So when we make this L measurement, it's very difficult to find this point, the lower end. Difficult to find the lower end because like transparent. But when the mercury is silver or something, the silver color. Oh, it's silver color. In that case, we can easily find the length. So this point and this point, easily we can find. That is another. Right? Also, water wets the glass. The final is water wets the glass while mercury doesn't wet the glass. So what does it? Why is this wetting the glass is considered? Actually, for higher response, quick response. Like when you change this could quickly respond. So if not, like if you change this and you will have to wait for a longer time until this water slides over, slowly it will slide because it wets the glass, slowly drags and changes the height. But mercury is not like that, quickly varies because like, it doesn't wet the glass. These are the 4 things that you need to remember. 4 things that you need to remember.